us are here, so while we await the other people, can we just do a quick recap of what you understood last class? Come sit here, this side. Parul. Aage, Parul. Just behind him, yeah. Weren't you already in? Okay, so a quick recall of what we did last class. Specifically, Shruti, Archita, and Meghna, were you the ones who were asking me the question after class, last class? Yeah? So, I went home, I thought a lot about what you understood, and I felt like there needs to be some more clarification. So, give me now what you think you understood, and let me just tweak that a bit. Prashad? So, Shruti, tell me what you understand by, so we'll skip all the part about DNA except what is the part of DNA that we look at when we look at DNA for forensic purposes? The junk part has a name. Yeah, which is? Non-coding region. What in the non-coding regions are we looking at?
The deposition.
Specifically looking from them because last class they had a bit of a clarification. So
We look at points of reference such as STR locations and whether it's repeating at the same locations in both these samples.
yes, okay. So in the junk regions, you do look at certain items that are repeated any number of times, and it's different for different people, allegedly. But to compare it to a crime scene sample, what does that need to be? Now at the crime scene, you can have any kind of sample. It could be cellular sample, it could be body fluid sample, or any kind of sample. So are your STRs always located at the same place across all your cells, cellular DNA? Nandini, why do you say no? You just wanted to say no. Just like felt like an answer that was the no.
I think there's a high probability that it will be at the same place, but to make sure we look at all the other chromosomes as well, and all the other cells in 22 chromosomes.
So STRs are basically locations. STRs are basically repeat units in between junk DNA. And there are many of those at various junk levels, okay? So one that is in Delhi, any junk that is in Delhi will have a certain number of repeats, but there can also be junk here in Sonipat. And there can be junk towards down near Panipat, okay? So these are locations. So there are some things called STR markers which locate them. There are several of these regions that we have found via research in DNA where things repeat. Is that clear? So yes, the location of them are fixed on the chromosomes like this. They are fixed on the chromosomes. For every chromosome 1, you will always find whatever the unit is here that is repeating, you'll always find it at this location called T-pox. So henceforth we are going to refer to whenever you see a DNA profile, it will have these names. One of the columns will have this name in the table. What does that mean? This is a location for an STR. The key word here is STR loci. Loci is Latin plural for from locus, which means location. Is that clear? So these locations are fixed and they are found on every chromosome. Is that also clear? The number of repetitions are different. So for me, TPOX might be 5. For Nandini, it might be 7. For Manan, it might be 9.
Is it similar for if you're related?
Some maybe, some will not be. That's how you are. So it's always the whole profile that will be. So you obviously you got this 5 or 9. Now, just a second. This is only one of your chromosomes. Remember, you have 2 because mommy and daddy. So maybe I got 5 from my mother and 7 from my dad. Okay. So if I have a sibling, they could have also gotten 5 from my mother and or 7 from my dad, or they could have gotten 5 from my mother and 9 from my dad because my dad is 7, 9. So just on one location, you cannot make a very clear clarification on whether they are different. You need a combination of those. So in some parts, in familial relationships, you might be similar but different in others. And that is why they say you have a unique profile. Is that somewhat clear? Yeah? So this is repeated in all your cells, all cells of your body. Which means at all cells, you will have 2 copies of chromosome 1. And on both those copies, you will have location TPOX. And in those locations, you may have different numbers or same numbers, whatever you've inherited. Is this bit clear? Now, what was your, is that clear? Okay. So Shruti, Archita, is this concept clear from last classes? Does this clarify what I mean by repeat finding? Okay? Fast, fast. Could anyone else now throw back this idea again at me once again? Parul, would you like to give it a try? Could you tell me what I just said? Could you clarify STRs for the class? Try.
I think that the last class I'm not very clear on that anyway.
You did not attend the
I
class?
did attend the second half.
Okay. Prashant, would you want to give it a try?
Actually, missed the first half of this one.
What?
Actually, missed most of this one. I was sending some email. I was upset.
This is just a recap of last class. So tell me what you understand by STRs. What are we looking at in the non-coding region when we are using them for forensic profiling? What are we looking at specifically? Try, give it a try. You were present in last
I
class.
thought I was.
Try.
Sorry, no answer.
Are you gonna go sit there? Behind, yeah. Anyone else wants to give it a try?
We're looking for STRs which are non-coding regions, these are all a part of the junk DNA. So you see so 2 chromosomes will be present on both, and location is same.
How would you say that if you were talking about this to a judge who doesn't know? You say something matches, you say, and the judge asks you what matches, and then the abbreviation STR comes up. How would you just explain that?
So when we're looking at chromosomes and basically the structure of the DNA, we have parts of it which we look at, which is the STR, and parts of
No.
No.
STR is present in the
That's good. So where did you go wrong?
STR is in the
Yeah, STR is in the
STRs are part of the non-coding region. Okay, so anyone who thought STRs and NCRs are different, it's not. NCR is a bigger section of junk DNA that does not seem to have a gene function. Within that junk, you have certain regions that are called STRs. Why are they called STRs? Because they are short tandem repeats. That should define what that is. So now, what would STRs be?
So that it's like the part that we can match, like, because they repeat themselves in a certain way and they're unique in that way. So this helps us like
They repeat themselves a number of times. Not in any way.
yeah.
They are just repeats of the same thing a number of times. And the number of times it is varies between that chromosome and the partner chromosome within your body. So chromosome 1A will be, say, 5 times, and chromosome 1B will be 7 times. But for all the chromosome 1As and Bs in your body, you will have 5 and 7. There won't be a chromosome 1B which is suddenly 9. Is that clear now? Okay? But between you and me, you may have chromosome 1A 5 and chromosome 1B 7, and I will have chromosome 1A maybe 5, but maybe chromosome 1B will be 9. Okay? And that's how I'm different. Does that make sense now? But the thing is, we can't just differentiate based on one of these STRs, so we get a couple of more of them. And we get them from all across the chromosomes, okay? So we get them from various chromosomes and we create what is called a profile. But before we get there, what a profile actually looks like, let's talk about how we get there very briefly. Remember, this is not the part you're going to be assessed at. As we mentioned, that's how you collect the DNA. We already did this part in body fluid examination. You collect the DNA from whatever the sample is. Either you take a piece of this and dip it into sterile water, 1 or 2 ml of sterile water, mix it, dissolve the DNA material out, or you swab it with a cotton swab and then put it back in a microfuge tube, okay? Either way, that's what you collect from the sample, from the crime scene. Moving forward, this is what we also talked about, so I won't go through the whole blood testing again because we did blood groups matching, yeah? But the first step to any DNA testing is to match the blood type between the sample that we take from the control, which is the suspect, and the sample that we get from the crime scene. Why? Siddhi? Yes, I could see you zoning out. Why do we do blood testing, blood type testing match before we do DNA profiling?
It's way easier to collect and it's sources wise as well.
Yeah, Avni?
If the blood group doesn't match, now you have to proceed to DNA testing, which is like, it's more tedious as opposed to just doing a normal blood matching. So first you just test the blood type to see if it's the same one, and then you can proceed.
Yeah, so both of you were right. That's why you do blood testing. It's quick, easy, and cost effective. Plus, the effect of it that if it matches, then it means that you should go on to do DNA, because blood type by itself is not very specific. But if blood type doesn't match, you can use that as an exclusion. Because if the same person gave that sample, their blood type should also match. So, is there any caveat to this question, to this situation? Would you have different blood types or DNA types if you had just undergone a blood transfusion? Why not?
Because they always transfuse the same type of blood. They wouldn't transfuse.
I said, would you differ on the blood type and or DNA? So your answer says that blood type will be a match because
Because you can only transfuse the same
because
blood type.
transfusion happens between same blood groups. Not true. I'm AB, so I can take from anybody. So I can take from A and B and AB. So do I leave A blood behind?
So basically, I think basically what happens is when you transfuse blood, you're not transferring it into the arteries, but into the veins. So essentially, it's going to go to the kidneys first, get filtered, and then it's going to sort of go to the rest of your body. So maybe that sort of gets cleaned out and replaced with
The transfusion?
No, so the blood that's transfused, right, goes like straight to your kidneys first, and then sort of gets purified, and I think so. I think.
I don't think so. You can leave it out because you would have taken from anyone.
Why don't you actually, this is your homework for the day, find out whether breast transfusion actually is there any scenario where you might be leaving behind DNA that is not yours but of the donors with respect to blood type and DNA. Those are two different things. Blood type is from your RBC, which is essentially not the cell that you get your DNA from, and DNA is from other cells, okay?
Is it related to somehow if a person's got blood cancer or something like that? So
It depends on why you have a blood donation does not matter. It's like if I am someone who has taken say 2 liters of blood and then committed a crime, am I leaving my own blood or am I leaving their DNA behind?
Ma'am, like you said, blood transfusion just needs red blood cells, so obviously you cannot leave behind DNA. And about AB, when we discussed this, only our body is not producing any antibodies, which means that it's not necessary that you just leave.
But that's just for me, okay? That's just for me, right? What about anybody else?
So if I take,
Is there anyone else here who is AB? If you wanna disclose that? No? Anyone here who's A? Do you know your blood types? You should. You're A. So anyone else who's an A? Right. So if she donates blood to him, he commits a crime, cuts himself on the scene, leaves some blood behind. Is he leaving only his DNA or some bits of her DNA as well?
But you get only transfusion of RBC and that is
It's homework. Homework. Stop solving it here. Take something home. Okay, I'll answer it next class if you don't come up. But yeah, this was just to get you interested because you seem very dead and zoned out already. So, okay, now back to what I was trying to say. First you do the blood testing because it's a good exclusionary test, which means that you can save on time, energy and money if the blood type is not a match. Okay? If it is a match, you're going to do proper profiling, which means that this whole procedure here is a visual representation. This is scientific gibberish, forget about it. What this means is you have intact cells which are broken down to release DNA, which in real life will look like this, okay? Do you see this? You might see this much more clearly when I give you the slides, but you see this whitish coagulant at the bottom of this murky white liquid? So a lot of cells, of course, went in to create this much DNA. So at the end of the whole process, which is just a protocol with fancy equipment and fancy chemicals, at the end of it, what you do get left behind is very visible DNA coagulation. This is not one cell, this is from millions of cells, but you get DNA, which means that all the cell walls, all the particular individual cells have broken down, and all the DNA and the nucleus have been broken down, and all the DNA inside has been filtered out. Essentially, at the end of the process, this is what has happened, okay? all the DNA from each of the cell has been taken out and put in the same box. Is that clear? The second step we do is start doing the filtering, but before that you must know if you have enough DNA to do the analysis. That's the process where you quantify. Why do you need to quantify? You need to find out how much of it is there, because depending on that, remember that method I mentioned earlier, the one that multiplies photocopy. So if the minimum limit is to have 50 copies to do a test, okay? But I have only 10. I must first count how much I have. Clearly I don't have 50, but how much do I have? That's that process. Once I know how much I have, I know how many copies or how many times to run the copier, the Xerox machine, to get 50 copies. Once that is reached, I can begin the analysis. The analysis is a very complicated process. I will not go into that. After that, you get something which is a graph, which is translated to a table, and based on the table, I mean, you can make it from the graph, but it's easier to do it on the table. From the table, the scientist makes an assumption or an interpretation of whether the samples given are a match or not. Okay? Now, how does the, okay, yes. How does the graph look like? Which one is the crime scene sample? Okay, who wants to be the crime scene sample? Okay. You can be the crime scene sample. Let me tell you how that works on a graph. Can we set this up for a bit? Oh, is this going to be showing white? Yeah, that's better. Okay. While that happens, can I give out some other 15 people can randomly pick, just 15 people put up hands, I'll give you certain profiles. These are made up profiles, not real profiles. But this is just a sample. You pass one there, and to Siddhi at the back, and to Shruti at the back, and her, and Shruti at the back. No one from this side is participating, but I gotta take one.
I'll take one from mine.
Somebody take one. It's more than enough. Oh, you did? Okay. So that's it. That's given, okay? You are 15 people, which is all the number of people in the world, okay? And I have a crime scene sample. Can we pull this? What do we do with this? Okay. Okay. So, for those who have a profile, you can see what it looks like. It's basically A, B, C, D, and some numbers written by it, right? Okay? So this is a very simplified form of what would be T-Pox, F7, CF1, you know, those names. Yeah, I'm just simplifying it. It doesn't matter what you call them, because like I said, those are location markers, okay? So, and any number of things.
Are the numbers written the number of repetitions?
Yeah, the numbers written are the numbers. So this will give you the location of the STR, and the number beside it will give you the number of repeats at that point. Is that clear? Now, what I have done is, usually you get a sample of like this. You get a number like this because chromosome copy 1, chromosome copy 2. Okay? To simplify, I have only put one number for you. Okay? But when we do the actual matching, we will talk about both the numbers. For now, let's talk about what is the, where's the, where are you going? It's gone. Lost. Anyway, what's your sample? What's the crime scene sample?
85.
Okay, it was 5, 7. Okay, so this is the crime seen sample, how do we represent it on the graph? Obviously it's a graph, so it's a two-dimensional representation. Obviously it's got two lines. Okay. Let's say there are that many repeats, okay? That many repeats possible in any location, about 10, nothing more than 10. That's not true. For this purposes, we're going to take 10 as the max limit of repeats that can be at a certain location. So, first I have to map the location, right? What is the location? So, no, sorry, I did this wrong. I mean, there's still a mapping there, but so the number of repeats is actually at the bottom, Nitya. The number of repeats is actually at the bottom, okay? So where would she mark for A?
X-axis, 5, 0.
5.
Not 5, 0, no, that is small, not 0, because I'm just working with 1. If it was, say, 5, 7, if that's what you want, we'll go there. First, you are going to only look at one section. So first A. So 1, because this axis is already taken, let's say this whole graph is for location A. Okay? So where would, she has number 5. So where would I put it on the x-axis? Over here? Now how do I draw?
7.
No. This is the number of copies. Okay? It's just a quantity. So let's say the number of DNA copies or number of cells that I was looking at is probably thousands. But for more simplification, let's say I was looking at 5. Okay? So the graph appears like this. Is that clear? This means that the number she has is 5 and about 500 copies are present. This is actually irrelevant. Except that we have something here called the threshold. Threshold means for you to consider that this is the actual number and not an anomaly, the peak must be above this minimum level. Why? I'll just tell you in a bit, once we look at a real graph, okay? Now, if she was 5, 7, how would that look?
Next one at 7.
Next one, how big?
5.
Has to be. Because why? We broke down 5 cells, okay? We broke down 5 cells, so as many copies of one she has, same number of copies for the other she'll have. She can't have more or less. Okay, so ideally, this is the same height. If she was 5, 5, how would that look? 5 cells, and she has 5 repeats on both. From 1 chromosome she gets this much. From 2 chromosomes she would get
The number of copies might
Yes. Who said that? Kshitish? Was that you? Right? It's still at 5 because she's got 5, it's just more. Okay? Does that make sense? No? This is basically the quantity, okay? Remember, the number of cells you have is always the same for every marker, okay? If you have 10 A's, you'll have 10 for location B, 10 for location C. It's the same cells that were broken down eventually to give you the DNA. Which means that if this was B, let's go to B. So they take a gamble. How would that look?
From 7 only first.
7? How far?
We still have 5.
Yeah, 5 copies. Go for it. 5 and okay, that bit is clear. So what is confusing? The 771.
Why did I just got confused when you said 2 5? So why did it?
Because if this is 7 7, how would that look? Okay, so 7. This 7 will get you how far? Till 5. Okay, but you have one more 7. The machine is not discriminating. It's not like this is mummy, this is papa, so I'll put it beside. The machine is, if it's 7, the machine is going to put it on the 7. So now how many other?
5 more.
Yeah, so there's more. So that's 10 copies. So it's usually double this peak. Is that clear? Now let's look at a real, I hope this is, oh, I'm trying to switch on the AC with the, too many remotes.
Professor,
Yeah.
please turn this a little up because it's cold.
Yeah, it's cold. Could you pass me the remote? And you can do that. Yeah, this gets a bit cold as well. Oh, I must connect. Disconnected to my things. Oh, it's confused. Just really connected. Yeah. Okay, so this is actually what an output from the actual machine looks like. So this will be attached as part of your report. And while it is not necessary that you know how to read it, it's always good. So this is a location, TO1, which is an actual location for an STR name. And over here, what is your alleles? What is your numbers? Forget I said alleles. What is your numbers? 7 repeats and 9.3 repeats, okay? At location FGA, what is your alleles? What's your repeats? 24, 26. Now, in your copies, can you start making a table with all the names and all the, just for a practice run, do it. What a real table would look like. So column 1 would be the location of the STR. They would be the names in yellow and green. And column 2 and 3, or you can just make it the same column, You have to write the numbers that are showing below. The rule to writing that number is the smallest number comes first and the largest number is behind. It doesn't matter whether 13 showed before, it won't show before, but it doesn't matter which comes from the mother or the father. The smallest number comes first, the largest number goes behind.
Excuse me, ma'am.
Yes.
That some samples have higher amount of copies than the other.
We will get to the anomalies. So hold that question. Can you just do the table for me now? Just create a table. That will be T-Pox DY-S391 D18 S15. And over here you write what are the numbers you see. What would the number for T-Pox be? Good. What would DY-S?
11.
Okay. What would the next one be? D18 S51. Okay, so like that, give me for everything. What would we have for DS31358? The first one. D3S1358. BWA? D16S whatever? CSF1PO? And what is this? The name hasn't clearly come up. In a bigger screen it will. What is this? This doesn't say a number. What does this say? Sex. Okay? So a melogenin is something that we get from your 23rd pair. Okay? So whether you're a XX or a XY, a melogenin is present on the X. Okay? Which means that, and on the Y. Which means that if you have an X, what would that show? This much. And if you have a Y, it would show 2 peaks. But if you were a XX, if you were a girl, how would that show?
Two separate weeks.
Would it show 2 separate peaks or a taller peak at X? How many quantities of X's are there? So at X, there'll be double the quantity. Is that clear? Think of this as a location. If you have only, then will it show. If you are XX,
It will have a double P. It will have a longer sort of.
it will only show at X's. So the only thing is that you will get more of this. Only if you have a Y will it move to the side and give you a Y. Is that clear? Okay? So a melogenin is different on the Y chromosome and different on the X chromosome. And depending on what you have, you will show different peaks. So this is very telling of what sex you are, or the crime scene or the donor are. What? Okay, so the question that he asked, how many copies are here? How many chromosomes are here in this case? Can you tell? 24, 26 is the number of repeat. Okay, so what does that tell you? There are?
This one pair of 2 pairs, it's a single pair.
See, over here, this is what you call the midpoint. This is the max. Over here you have this 500, which is missing kind of from here, but it will be in the middle of this. This point, that's your 500, that's your threshold. That's your threshold level. Peaks have to exceed beyond the threshold level for the computer to consider it. Is that clear? Are these real peaks? Are they considerable? Yes. Why? Because they exceed the threshold level. But they are different. You are telling me that that individual has 24 and 26, right? So they must have equal copies of both. Because if I break down 5 cells, I'll only get 5 copies, right, of both. So 5 copies of 24, 5 copies of 26, which means my peaks must be at the same level like 14, 15 is, right? But here it is not, right? What's going on?
Oh, is it? No, I'm not very sure. I think, is this like an indicator of like Down syndrome or something where like there's a lack of chromosomes, I guess?
No, Down syndrome you can easily tell by a variation of this. And remember, the first rule of using DNA for forensics is to not look at things that can tell you something about your gene function, medical health. So whatever gives you the information about Down syndrome is definitely not included in this profile. Hold that question that I gave you. Look at these tiny bumps. What are these? There are many of those across. Why is that not a straight line?
Are those the ones that were lesser than the threshold ones which are not?
They are lesser than the threshold, but you can only have 2 because you are a double chromosome paired person, right? That's how humans are. We only have 24, 26 clearly on our chromosomes. So where is these tiny peaks coming
Is
from?
it 24, 24, but it's like the same and it's, instead of 2000 it's 1000 is possible. Is it that?
No, then you would be double 20, 24, 24 and 26. Then you would have 3 chromosomes, which is not what people are. People only have 2 chromosomes. What is this tiny peak? They are there everywhere. You can see them more there.
I'm not sure, but I think the submissive ones, they don't, like, they are like 2 pairs, right? One which will show their characteristic and one which will not show their.
But both of them are being shown. This is called residual DNA. Okay? Residual DNA, because remember, is the same machine at an institute, at any testing lab. It's the same machine that is doing this testing 10,000 times maybe, okay? And the process is between each new sample, you clean it, and there is a process to clean it. But all the time, it can happen that the cleaning is not done properly. Which means some tiny bits of what you ran through the system before can stay behind. Of course, they will not, or they shouldn't, if the cleaning is done even somewhat properly, they will never cross the threshold, which means that the computer itself will discard them as being residual DNA, like things that were left in the machine from the earlier test, which are not from this sample. Okay? So sometimes any tiny peaks that you can count that does not cross the threshold level can be from residual DNA. Secondly, it could also be from the DNA sample that you picked up. If you don't know for sure, I don't know what sample this is this a control sample or a crime scene sample? If the crime scene sample is starting to degrade a little bit, that means part of the DNA got decomposed, so there were lesser number of 26 but more number of 24. One explanation is that. Secondly, if the sample got mixed, somebody spat on my arm and you took a DNA of it, okay? So when you were taking the sample, you mostly took most of the saliva that was on it. but you will collect a little bit of my skin cells as well. Maybe one of the things that I have is a 24, which is kind of adding to the already present 24 from the perpetrator. And maybe the other one is a 22, which is not showing, so it's a tiny peak here. But the 24 is increasing. Does that make sense? You have to know why things can go wrong in the reading as well. And this is why. Sometimes the machine cannot be cleaned enough, so something may be left behind from previous testing. Sometimes the sample may not be as pure, so you can get a little bit extra. So while you see these things are not all the same marks, but the good thing here is the computer is trained to keep in mind these anomalies, these problems. All you have to look at any of these points, despite this not looking like an ideal graph, is if the computer is saying it's 14, 14, 14, 15, that's what you need. Trust the computer on this one.
So if you get somewhere, if the DNA is getting mixed up, then the graphs, they get added to the same equation.
If it's the same point. If it's the same number of repeats, it'll get added. If it's not the same number of repeats, you get a blip on the side. Okay? So this was an explanation of exactly what I said. And this is how a matched profile looks like. Okay? So you have two suspects and this is what your evidence says. You make a table like this and you get a profile. So which one clearly matches? Which are the two numbers that clearly match to the evidence? S2 matches. Okay? Now that's how in most of the criminal cases where you're trying to identify who done this, this is how you will match. Collect the sample from the evidence or from the crime scene, collect the sample from the possible number of suspects, and they should be a clean match like this. Okay? Is that clear?
Is there a minimum number of STGs that you need to match?
STRs?
STRs.
That comes with the kit actually. So earlier when we hadn't discovered a lot, it was 10. Then we made a new kit that was 13. Now the most common kit is 16. So the standard kit in most state labs would be 16, even internationally. However, there are two extra addendum things that are available to test. You have to buy them separately because they came into the market very recently. So they've not been incorporated in the kit. But slowly we are also now looking at 2 more, 3 more possibly. So the max we can get is possibly 22 because 23 because we have that many number of chromosomes. So right now we are at the possibility of 18. I know my friends have worked on markers, STR markers for 19 and 20. But that's not, the science is still like in process. But yeah, and then very soon somebody will work on 23rd and that'll be it. We'll have exhausted 1 marker from each chromosome. Is that clear? Did you kind of get this? I'm not sure. Take a break, shake your head, come back. We'll revise this again and then see what the problem is with mixed DNAs and partial DNAs. Okay?